Okay, so these are the notes for Module 14.3 and 14.4. Again, we're working with angles and parallel lines. And so to start with, we have some key vocabulary. The first word being a converse. Now, these aren't the shoes that you like to wear, but it's talking about an if-then statement. And so in an if-then statement, right, you have if something happens, then there's a result. This is also known as a conditional statement. You may hear that word as well. Okay, the conditional statement is also just an if-then statement. So to give you an example, we have a theorem here that says if two lines are parallel, then same side interior angles are supplementary. So the converse to that would just be simply switching those two ideas. So it would read if same side interior angles are supplementary, then the two lines are parallel. Okay, so I'm sorry there's not a ton of room there, but that gives you the idea. Okay, you simply take the if statement and the then statement, and you just flip-flop them. And so if you read this next section, when would we want to use the original as a justification, and when would we want to use the converse? Well, again, the original, if you remember back to 14.1, 14.2, right above that table on the bottom page, says if the two lines are parallel. Okay, it has to always start with if the lines are parallel. And so the original statements always say if these lines are parallel, if you know they're parallel from the graph, from the diagram, from information in the text, then you know that the angles are supplementary or congruent, depending on what they are. The converse would simply be if you can tell and prove that those angles are supplementary or are congruent, then you can verify that the lines are parallel. So it just kind of depends on the situation and what you're given. If you're given the fact that the lines are parallel, okay, first, then you would be using the original statement. Versus if you don't know that they're parallel and you're trying to prove that they're parallel, then you would have to use the converse. Okay, so example 1, a mosaic designer is using quadrilateral shaped colored tiles to make an ornamental design. Each tile is congruent to the one shown to the right, which is that tile right here. So it says, look at this situation, use the values of the marked angles to show that the two lines are in fact parallel. So if you look at the diagram right here, okay, you'll notice that those lines aren't marked parallel. They look parallel, right? They're drawn pretty straight, but we don't know for sure. And so if we were to put that ornamental design, or that tile, into our design here, okay, angle 1 would match up with the bottom right corner, which would be 120 degrees. And angle 2 would also be 120 degrees. Oops. And so the relationship between those two angles, if you think back to our last unit here, is that those are corresponding angles. And again, we want to look at that relationship and say, okay, we know that those are corresponding angles. They are in the same location. Right, they're kind of in the top left of their intersection here. So here's one intersection and the second one. They're both in the top left, so they'd be corresponding. And according to our theorems, corresponding angles should be congruent, corresponding, congruent. And so we want to look and say, okay, are they congruent? Yes, they are. They're both the same. So the conclusion would be, because our corresponding angles are congruent, then our two lines L1 and L2 are parallel. Okay, so it's again using that idea of I don't know that they're parallel, but if I can see those relationships, and if those relationships are true, in this case the corresponding angles being congruent, then we can say the lines are parallel. So example 2, explain why the lines are parallel given the angles shown. Assume that all tile patterns are this basic shape. I apologize, I don't know what happened there. Weird typo. But I'm going to have you pause this for a second and go ahead and try to fill this one out, and then I'll go over the answer. So again, if we put that tile into these two spots, you'll notice that the 1 would line up with 120 degrees there, and that the 2 lines up with the 120 degrees in that corner. And angles 1 and 2 themselves have a relationship, and those are that they are alternate interior angles. And so again, alternate interior angles are supposed to be congruent, and since they are, in this case, because alternate interior angles are congruent, lines L1 and L2 are parallel. And that is called using the converse, because we didn't know that they were parallel, and we said, okay, since we know those relationships with the angles, then we can say our lines are parallel. Okay, so that's an example of using the converse. And again, if those alternate interior angles were not congruent, let's say that they were supplementary and added up to 180, well, we know that alternate interior angles are supposed to be congruent, not supplementary, so if they ended up being supplementary, that wouldn't work. We wouldn't be able to say that those are parallel. So then on the next page, if you flip the page, again, we have some key vocabulary. This is now getting into 14.4. If you are trying to look back in your notes during some of the homework. So for some key vocabulary, you should already be familiar with these, I believe. Perpendicular means that they meet at a right angle. The symbol for that looks like an upside down T. That means that they are perpendicular. Something, if it bisects something, means it cuts it into two equal halves. And a bisector is simply a line that cuts another one into two equal halves. So therefore, if we kind of combine all of those ideas together, a perpendicular bisector is a line that cuts another line in half at a 90-degree angle. Because you can have a line cut another line directly in half. Right? Both of those sides are pretty darn close, but you can see that that's obviously not a 90-degree angle. And so a very specific line that meets at a 90-degree angle is called a perpendicular bisector if those sides are the same. Okay? So the perpendicular bisector theorem, if a point is on the perpendicular bisector of a segment, then it is equidistant. Hopefully you remember some root words from your time in English class. Equa meaning same, distant meaning distance. So it simply just means the same distance from the endpoints of a segment. So if a point is on the bisector of a segment, so for example, if I have some point over here, it's on my perpendicular bisector, we'll call it point P, then the distance to the left endpoint, we called that L, would be the same as the distance to the right endpoint, if we call that R. Okay, then those two lines would be the same distance, is what that is saying. So now if we want to write the converse of that, go ahead and try to write the converse of that, now that we've talked about converses and we have the theorem in front of us. So go ahead and pause it for a second while you try to write that down. And so the converse of that would be if a point is equidistant from both endpoints, then it lies, it lies on the perpendicular bisector. So example 3 here, I actually want you to try this one first. Okay, I know this is kind of the only example on this page, but pause it for a moment and see what you can come up with. Read the problem and see what you can find if you can solve it on your own. So the problem says if AD is 10 feet long, so AD is 10 feet long, and BD is 6 feet long. So BD here is 6 feet long. How long is AC? So I want to know how long is this bottom line down here. Now, first of all, one of the first things hopefully you did was notice that AD is the same as DC, and so therefore DC is also 10 feet. And because of that, right, we see that we have this 90-degree angle here. And the problem is I need to know what the bottom line is, kind of that base line. And so for that, okay, think of this as only one triangle. Kind of block off just one triangle here. And you should remember something about a right triangle. And if you have one length and another length, that you can find a missing length, something called the Pythagorean theorem. By now you probably have that memorized and will never forget that for the rest of your life. You're welcome. You can thank all of your math teachers ever. A squared plus B squared equals C squared. And so, again, the only one that's specific is the C squared, has to be the hypotenuse. So that's going to be 10 squared equals, and then these don't really matter, A squared plus 6 squared. So A squared plus 36 equals 100. A squared equals 64. Because we subtracted 36 from both sides. And then, again, the last step, square root, A equals 8. Now, the tricky part, though, is that 8 only represents this side right here, BC. And so the problem doesn't say find us BC, it wants to know, well, what is AC? And since this is a perpendicular bisector, because that is equidistant, right? We said if that line that point D is equidistant from the endpoints C and A, then it must be on the perpendicular bisector, meaning that AB is the same as BC. Now, if we don't know that those two are the same, then we can't really say that. Yes, it would look like it's cut in half, but again, we don't know for sure. But in this case, we do. So since BC is 8 feet, AB is 8 feet, which means AC is 16 feet. Okay, so that kind of combined a lot of different ideas here, right? The idea of the converse, and the perpendicular bisector theorem, and the Pythagorean theorem. Okay, so all of that stuff still applies, and it's kind of at the point where we start to combine a lot of this stuff within each problem. Okay, so if you guys have any questions, please ask me tomorrow.